Welcome back to the next video, everybody. Today's video is the conclusion of our discussion on how the irreducibility of rho bar E3 for an elliptic curve E over Q implies the modularity of rho bar E3. So we covered the first three steps last time. Let's recall. We were trying to show that if we take Langlands-Tunnell for granted, that rho bar E3's irreducibility implies its modularity. So the first three steps we took last video were we extended rho bar E3 to a complex representation rho from GQ to GL2 of C. Step two was we showed rho satisfied the conditions of Langlands-Tunnell. We had solvability, we had oddness, we had irreducibility. And then step three was by Langlands-Tunnell, we found a new form which we called G with Fourier coefficients B sub n in S1 gamma 0 of N1 epsilon 1 for some N1 and epsilon 1. With BQ equivalent to Q plus 1 minus the number of FQ points on E mod frac P for almost every prime Q, and for some prime frac P of Q bar lying over 3. And so this gives us, by definition, that rho bar E3 is modular, but the problem is that it's modular of weight 1 according to these results, and we want it to be modular of weight 2. And so that's where the last step, step 4, comes in today, and that's what we'll cover. Okay, so step 4, then, to conclude, will be we need to find a modular non-cusp form E naught of weight 1, such that E naught is equivalent to 1 mod 3, and the product G E naught with Fourier coefficients C sub n, so this cusp form, is of weight 2 for some level n in character psi. And it will be such that Cn is equivalent to Bn mod frac P for some prime frac P of Q bar lying over 3. So the new Fourier coefficients will be equivalent to the old ones. Okay, so here's the selection. We'll take the Eisenstein series E naught of Z equals E1 chi of Z, which is 1 plus 6 times the double sum over the natural numbers and the divisors d of n for each natural number n of chi of d q to the n. And what is this chi of d? It's an odd Dirichlet character mod 3, odd meaning -1 maps to -1. And it's given explicitly by chi of d is equivalent to 0 if d equals 0 mod 3, 1 if d is 1 mod 3, and -1 if d is -1 mod 3. Very easy to remember. Okay, and most of the properties we need this to satisfy are not hard to show. For example, it's easy to check that E0 is an M1 gamma 0 of 3 chi. It's also easy to check that GE0, GE naught is an S2 gamma 0 3N1 epsilon 1 chi. It's also easy to check that each non-constant Fourier coefficient of E naught is divisible by 3. In fact, it's divisible by 6. And so it's then from there very easy to see that C sub n is equivalent to B sub n mod frac P for the frac P that we gave above on the first slide. And if you want more information on Eisenstein series because you're not familiar with the general theory here, I recommend Diamond and Sherman chapter 4. Okay, so now what's the problem? Well, the problem is that GE0 is the product of a new form with an Eisenstein series. It's of weight 2, just like we want and everything. The only issue is we need it to be an eigenform to actually conclude that rho bar E3 is modular. We got the weight 2 part, we got the cusp form part, we don't have the eigenform part. If it would have been an eigenform, we'd be done and rho bar E3 would be modular. So how do we fix this? Here's where you have to refer to Deligne and Sayre's non-trivial weight 1 construction, they call it. And here's a lemma from that construction. It's the lemma we'll need. It says, let F1 be a normalized cusp form in SK gamma 0 n psi for some n in psi with Fourier coefficients C sub n. Let K over Q be a number field such that the ring of integers OK contains all of the Cn and all the psi of n's as usual. Let frac P be a prime ideal of OK containing 3 such that F1 is a mod frac P eigenform. What does that mean? It means there should exist B sub n such that T sub n F1 is equivalent to B sub n F1 mod frac P for all n, where the T sub n are the Hecke operators for this space here, the SK gamma 0 n. Okay, what's the conclusion? The conclusion is you can actually find a normalized F in SK gamma 0 of n psi and D sub n such that for all n, T sub n F actually equals D sub n F, and then D sub n and C sub n are equivalent mod frac P prime for some prime frac P prime of OK containing frac P. So you can actually lift this mod P eigenformness, let's say, to an actual true eigenformness that isn't just a mod frac P, let's say. Okay, so I like 2 different references for this. I mean, there's Deligne and Sayre's actual paper, which I'll call DSFM 6.10. And then there's Laga's modular forms of weight 1, chapter 3. And there are various other expository notes on the Deligne and Sayre construction. Okay, so the stunning conclusion is this. Just apply this lemma to the weight 2 modular form GE0, right? And what you find is that since E0 and G are normalized, GE0 is normalized, so C1 is 1, where C1 is the first coefficient of GE0. Let K be the number field of GE0, so that's the number field kind of generated by the Fourier coefficients and the character values. And let frac P be a prime ideal of K lying over 3. We know E0 is equivalent to 1 mod 3. That was one of the defining properties of E0 that we wanted. And so if we set F1 equals GE0 from the Deligne-Serre lemma, we end up finding T sub n F1 is equivalent to B sub n F1 mod frac P. And the reason for that is simple. I mean, T sub n G is equal to B sub n G for all n. We already know that. Okay, combined with this fact. And so the lemma actually applies to our F sub 1 then. Well, what does the lemma give us? It gives us a normalized F in S2 gamma 0 n psi and AP, let's say, such that TPF equals APF, and AP, which will be equivalent to CP, which is equivalent to BP mod P for all primes P. Okay, but then what is this? I mean, if you just unwind all the definitions here and use facts we already know from this video and the previous video, what this says is that for almost all primes Q, A sub Q is equivalent to Q plus 1 minus the number of FQ points on E mod frac P prime, or some frac P prime in OK containing frac P, and this is exactly what we wanted. This gives us the modularity of rho bar E3. Okay, so next time we're gonna, so we have finished proving the piece of the proof of Fermat's last theorem that we needed, assuming Langlands-Tunnell is true. So now we have to start looking into the proof of Langlands-Tunnell. We also have to start looking into the equivalence of the automorphic form of Langlands-Tunnell to the kind of standard, more usual form of it. And we also have to develop kind of a ton of background and definitions and place this all within a much larger framework, which is the framework of the Langlands program and the Langlands conjectures. And so we'll start doing all that next time. So thanks for watching, and I'll see you then.